the uncertainty principle, a thing called the Casimir effect, and hopefully a little bit about black holes as well. So I guess we have to start with the basic physics, which is the uncertainty principle. It's this weird thing that you can't measure the position and the momentum of a particle at the same time. And actually for this video, the important one is you can't measure the time of something and the energy of something at exactly the same time. So if you've got a photon, you can measure exactly when it arrives if you want, but then you don't know what its energy is, or you can measure exactly what its energy is, but then you don't know exactly what time it arrives. And there's a fundamental uncertainty in that energy, which works even if the photon has zero energy. So if the photon fundamentally has zero energy, then there's an uncertainty that actually you can't tell whether it's zero energy. It could actually have some energy. So that means that a photon with zero energy isn't there at all, basically. You've got nothing there. And that means that even when there's nothing there, you can actually have a photon with suddenly acquiring an energy. And that leads to this weird effect that even in the vacuum of space, you can have photons popping into existence for a brief period of time. So basically you can sort of cheat nature. You can borrow energy as long as you put it back before anyone notices. And that's this trade-off between the amount of energy you've got and the amount of time you've got. And the more energy you borrow, the less time you can borrow it for. And that means that the vacuum of space is actually this seething mass of particles and antiparticles being created. There are some rules so that you have to kind of create particles in pairs. But beyond that, even in the vacuum of space, you can have particles popping into existence and disappearing again. So this idea that vacuum is empty is actually not correct, right? That even in vacuum, you have these virtual particles that appear and disappear. So it applies to every particle, absolutely anything. So I was talking initially about photons, but you can do it with electrons and positrons appearing. You can have protons and antiprotons. You can have anything you want, but obviously the more massive the particle is, remember from Einstein's famous equation, E equals mc squared, the more massive the particle is, the more energy you're borrowing to create it. And therefore the quicker you have to put it back before anyone notices. So the least massive particles can exist for the longest periods of time.
You couldn't create like a planet or a gold nugget. These are...
In principle you could create anything, but of course by the time you get up to what on this cosmic scale of things are then very large masses, then they disappear on such a short time scale that really they effectively don't exist. It sounds like it's made up, but actually there are experimental tests you can do to show that a vacuum is actually a seething mass of particles. It's not empty space. There is this famous experiment, a phenomenon thing called the Casimir effect that was predicted way back in the 1940s that says that if you do an experiment where you've got two plates very, very close together, so about a micron apart, so 10 to the minus 6 meters apart, then actually what happens? Well, you've got this seething mass of photons being created out here by this uncertainty principle, and you've actually got photons being created in the gap between the two plates as well. But the interesting thing is because you've now got this pair of plates, that actually restricts the kind of photons that you can create. You can't, for example, create light with very long wavelengths because it wouldn't fit into that gap. So just by having a pair of plates, although this effect is still going on, you create fewer particles in the gap in between than you do out here. Now the photons out here bouncing around and hitting the plate exert a pressure on it. And the photons in here bouncing around that are being created by this virtual effect create a pressure this side. But of course now we're creating less photons in this gap, which means there's a bigger pressure this side than there is on this side. So there's actually a force. And this force has now been measured that you can actually detect this force. You set up this experiment, you can actually detect this force and the plates actually get pushed together by this effect called the Casimir effect, where you're actually seeing this effect of the virtual photons being created, this seething mass of virtual particles, but just more of them on one side of the plate than the other. It explains things, but the main thing it does is creates a huge problem. Because if you're a theoretical physicist, you can do a calculation that says, okay, so I'm creating all these virtual particles, they've got mass associated with them. How much mass am I actually creating in the universe that's just from this stuff popping into existence? And the answer is, unless you're very careful how you do the calculation, you end up with an infinite mass. And so it's actually one of these problems that theoretical physicists have, that if you do a naive calculation of just says, well, let's let this effect go, what's going to happen? And the answer is you end up with a universe that just doesn't work because you end up with infinite mass density everywhere and the whole thing, you get infinities appearing in your mathematics. So theoretical physicists have to do all this clever maths using a process called renormalization, which basically is a way of kind of shoveling all those infinities under a rug and not worrying about them anymore.
I get the impression this must be a very faint phenomena because, like, for example, when a rocket ship's going to the moon, it's not running into a barrage of particles that keep popping into its path.
Well, it is, but actually you're right. The impact it has on the rocket is tiny because the forces involved are very tiny. And that's this effect of this, again, if you just do a naive calculation that says how big should this effect be, if you're not careful, you end up predicting that it should be a huge effect. And somehow it ends up being normalized down to this very small effect. But it is, you're right, it's a pretty small effect in everyday life.
Okay, You did promise me black holes.
Okay, so we need to do another thing before we get to black holes, which is was the Casimir effect. Now, there's a thing called the dynamical Casimir effect, which says that, okay, so if I've got this pair of plates, then this phenomenon goes on and we have these virtual particles being created out here and on either side, but there's fewer in here, and that creates the force. Now, the dynamical Casimir effect says that actually, if you think about the virtual particles being created in here, if I accelerate one of the plates very quickly, so instead of just having them sitting next to each other, I move it backwards and forwards very quickly, some of those virtual particles become real. So actually the things which were popping in and out of existence, some of them actually become real particles. And there's two ways to think about this. Either you can think about it of saying that actually when you wrench them apart, that these little pairs of particles which pop into existence and then recombine and disappear again, they kind of lose track of each other because they kind of get pulled apart as well.
They lose their twin.
They lose their twin. Or alternatively, if you want a duller explanation, you can say that actually the interaction of the kind of the electromagnetic field you're creating in this space and the metal plate, when you accelerate it, ends up creating photons from the surface, and the photons are then emitted from the surface. But either way, in some sense, the energy that was originally in those virtual photons in the gap gets converted into real photons. And you haven't cheated. It seems like you're getting energy for nothing now, that you haven't paid back the debt. But actually you have, because in order to accelerate this plate, there's a force, remember, and when you accelerate something against the force, you end up doing work. So actually just pulling the plate backwards and forwards puts energy into the system. So you're not cheating nature. And for a long time this was thought to be this was just a thought experiment. And the problem is, from an experimental point of view, that actually you have to move the plate at relativistic speeds. So the plate that you're moving backwards and forwards has to move at some decent fraction of the speed of light, which you just can't do with real plates. But actually, just a couple of years ago, someone did a very subtle experiment where they, instead of having a pair of plates and a gap in between, they kind of created an electronic analog of this, which is they had a waveguide, which is just something that kind of forces photons to travel in one dimension. And at one end of it, they put one of these things called a squid, which is a superconducting device, where by changing the properties of the squid, you can effectively change the length of the waveguide at whatever speed you want. So they could actually drive it at like about 5% of the speed of light. So get up to a speed where actually they were effectively changing the gap, this kind of cavity at those kinds of speeds. When they did that, they found that this cavity started emitting microwave photons. So actually the effect has finally actually been detected in 2011 for the first time. So that then gets us on to black holes. A black hole, obviously, you haven't got accelerations in a black hole, but you've got gravity. And there's this thing in general relativity called the equivalence principle that basically says that the way gravity behaves is indistinguishable from the way that acceleration behaves. And actually, anyone who's ever stood in a lift is familiar with this, in that when it starts going up, when you start getting accelerated upwards, you feel heavier. And actually, you've no way of knowing whether the gravitational field, unless you can look out through the window, you've no way of knowing whether the gravitational field of the Earth has increased, which is why you feel heavier, or whether you're being accelerated, which is why you feel heavier. So anything that, basically the physics of acceleration and the physics of gravity is very similar. So in a black hole, you don't have accelerating plates, but you have gravity, plenty of gravity. And exactly the same thing happens close to the event horizon of a black hole, where you have this gravitational field, that basically the virtual photons that are popping into an existence and disappearing around the black hole lead to real photons being produced. Now, again, you can think about this two ways. Either you can say that this interaction of the electromagnetic field with the event horizon of the black hole makes the event horizon emit photons, or you can have the rather more romantic picture that these pairs of photons are being produced and then disappearing, but actually once in a while one of the pair falls into the black hole, and then the other photon is kind of doomed to never find its friend ever again and has to wander the universe forever as a real particle. But it's exactly the same physics as what's going on. Now here, then the question is, how do you repay the debt? Because now you've created energy, and now you no longer have acceleration, you no longer have things moving backwards and forwards. There's actually only one place that the energy can come from, which is from the mass of the black hole, because the energy is mass times the speed of light squared, so the mass of the black hole is a source of energy. So what has to happen, bizarrely, is you've got something falling into a black hole makes the mass of the black hole decrease over time. And this is this process of a black hole effectively emitting photons, and in the process of emitting photons losing mass is this thing called Hawking radiation, and why black holes eventually, if left to their own devices, will evaporate.
I gather from that all black holes are doomed to evaporate away because they can't help this thing happening at their event horizon.
But so that's certainly true, but there are two things to bear in mind. Firstly, it's an incredibly slow process, which means that actually, black holes which form very early in the universe, unless they're really low mass black holes, won't have reached that stage even today. And the other thing is that actually that's how a black hole loses mass, but of course a black hole can always gain mass just by stuff falling into it. And almost certainly most black holes in the universe, there's more stuff falling in than they're actually losing by this evaporation process. So actually, even though the process is always there, probably most black holes are actually putting on weight rather than losing it. I mean, it's never been detected directly, so in that sense it's just a theory, but actually it's a pretty solid theory in the sense that all the physics that goes into it is we're reasonably comfortable with. There's something slightly uncomfortable about this whole area of physics because you're combining gravitation with quantum mechanics. So you've got the gravity of the black hole, you've got the quantum mechanics of these virtual particles, and it's well known that there's a missing piece of physics that we don't really understand how to put quantum mechanics and gravity together. But from the limited understanding we do have, it looks like this is a pretty solid result that actually black holes will indeed evaporate by this process. And we've got a little detector here. So in simple terms, all you're doing is you're firing some light up there, it bounces back and gets detected, and then you've got a little thing that says, okay, whenever I detect some light, I'll send another pulse up.